Welcome back to Miss Eddie's Math Movies, where it's a cute to be a square. Today's lesson is on section 3.6, which is more about parallel and perpendicular lines. By the end of today, you should be able to identify and have reasons for which lines are parallel and perpendicular. Before we start talking about parallel and perpendicular lines, we're going to talk about a construction. Construction is more than just what you see builders building houses and buildings. It's also a geometric drawing using only a compass and a straight edge. We're not going to worry about this one right now. If we have time, we will come back to it, but we're not going to do the construction today. We are going to learn some more rules about parallel. Remember, postulate just means rule. We're going to learn some more rules about parallel lines. So if there's a line, I'm going to draw this over here for you. If there's a line and a point not on the line, then there's only one line that goes through this point that's parallel to that line. If I were to draw the one parallel line, there's no others that we could draw through that point that are going to be parallel. Similarly with perpendicular, if we have a line and a point not on the line, and if I draw a perpendicular line, that's the only perpendicular line through that point to that line. I couldn't draw one over here. That's not going to be perpendicular. Even if I get really, really close, that's not going to be perpendicular either. There's only one point or one line that makes M and L perpendicular. Now this one, if two lines are parallel to the same line, then they're parallel to each other. So let's think about this. If Q is parallel to R and R is parallel to S, then Q is parallel to S. This should sound familiar to a property that we learned a while ago called the transitive property, where you cut out the one that's in the middle. Notice R was in there twice. So we can cut the middle one out on Q. It's parallel to S. This one is similar. In a plane, if two lines are perpendicular to the same line, then they're parallel to each other. So if M is perpendicular to P and N is perpendicular to P, then M and N are parallel. Not perpendicular to each other. So it's a little bit different. Also kind of looks like corresponding angles. Kind of what it looks like. Since we skipped the construction, we're going to skip this as well. Using properties of parallel lines. In the diagram at the right, each rung of the ladder is parallel to the rung below it. So L is parallel to M is parallel to N, and N is parallel to the ground. Explain why the top is parallel to the ground. Well, we know L and M are parallel, and M and N are parallel, so we can cut out the one that's in the middle, which is M, so L is parallel to N. And what else? We know that N is parallel to F, and here we go, we're going to cut out the one in the middle again. L is parallel to N, and N is parallel to F, so L is parallel by F. We use that theorem 3.1, which is like the parallel transitive theorem. We're cutting out all those that are in the middle. This one's kind of a review of what we've done before. It wants us to make the lines parallel. So if we look here, we want these two lines to be parallel to each other. Then, let's see, they kind of give me consecutive interior angles here. And I know that consecutive interior angles have to equal 180. So an equation I could write is 2x plus 2 plus 90 equals 180. Don't forget about that 90. Subtract 92 from both sides. We're left with 88. Divide by 2, x equals 44. So there's one way of solving it. Or if you know this is 90, you realize that up there has to be 90. But you end up with the same answer either way, doing the same process. Because they're both perpendicular. All right, on the checkpoint, to explain why A is parallel to C. Well, these symbols right here tell me that A is parallel to B, and these symbols here tell me that B is parallel to C. So using theorem 3.11, which is that transitive property with parallel lines, using that, and cut out the one in the middle. A goes to B and B is parallel to C, so A is parallel to C. That was theorem 3.11 that we just used. All right, then we'll just do this one together. Well, this is 90, that means this is 90 here. And these two angles are corresponding. And if we want these lines to be parallel, our corresponding angles are supposed to be equal. So 5x plus 10 is supposed to equal 90. I subtract 10 from both sides. I divide both sides by 5. I'm left with x equals 16. On the next page, we're recapping all the ways that we just learned to show that lines are parallel. So we have 6 ways now to show that lines are parallel. We can show that the corresponding angles are congruent. We can show that the alternate interior angles are congruent, or the alternate exterior angles are congruent. This is our special one. We want the same side interior angles to equal 180. That's our different one. Right, that's the special one. It has to be supplementary. So maybe you can remember same side supplementary, all those S's in there. Another way is this is the transitive, parallel transitive theorem we learned. If both lines are parallel to a third line, or if they're both perpendicular to a third line. These are the 2 that we learned today. But those are the 6 ways that you now know how to show that lines are parallel. This is M cubed signing out.